Okay, so I want to keep going with this and pose a question. We need to consider if this solution is an acceptable eigenvalue equation. So this solution specifically, okay? So one way that we could do that would be by using the momentum operator and operating on psi and seeing if we get a single eigenvalue out of it. But we won't run into a problem almost right away. Check this out. If I go h bar over I times d dx of this equation, which we know is root 2 over L, times sine n pi x divided by L. So remember, when I carry out this operation, it's supposed to return to me an eigenvalue, but also it's supposed to return the original function. So in other words, what that means is I'm going to have to get here some eigenvalue that I'll represent by omega, but then I'm going to have to get back my original sine m pi x divided by L equation. And hopefully you can see right away that's not going to work because the first derivative of sine is cosine. So this becomes a problem. Is it a problem that we can correct? The short answer to that is yes. And we can correct this problem by using the Euler relations, okay? So in other words, now if we reimagine this wave function that we've come up with, here it is, the wave function for our particle in a box, okay? I can rewrite sine as the following. So 1 over 2i times that normalization constant times e to the ikx minus e to the negative ikx. So this is the same two equations, okay? And now what's really cool about this, look at this. This is a linear combination of exponential functions. That means it's a superposition, which is really cool. And what's also really cool about this, we've already established using this generic wave function, right? E to the ikx plus b e to the negative ikx. I know that these aren't quite like in the same form, but as far as like a general solution, they are. They're in the same form, okay? So what's really cool is we established earlier this notion of e to the ikx and e to the negative ikx. That describes a superposition of particles moving left and right, okay? So the psi plus state, right, we know describes particles moving to the right. The psi minus state, of course, describes particles moving to the left. So just built in naturally to this function, this sine function that I'm going to separate right here, this already describes a superposition of eigenstates. So this error that we ran into here, yeah, that's an issue, but it's an issue that we can basically move right past. If instead of thinking of this as a pure sine function, we recognize that really this sine function is a superposition of these eikx, e negative ikx functions, which we also established describes particles moving left and particles moving right. And this gets even cooler now. If you're following with me, I hope that you are. Stick with it here. If now we were to look at the expectation value of particles in my box, okay? So I'm establishing here the sine using the same wave function, okay? And we could use the sine version or we could use the superposition version. It doesn't matter because we'll get the same result. The expectation value for the momentum of the particle in my box is 0. Does that make sense? Well, I think it does, because if I look at my particle right here, okay, we know that the particle is free to move in either direction. And we established here when n is equal to 1, so here I'm showing you the wave function. But now if I just go past this and I look at the wave function squared, right? We know that it's all positive values. Look, that wave function squared is telling me the most likely place to find that particle is right somewhere in the middle. So why is it that the expectation value of its momentum is 0? Well, that's because it's moving perfectly in this direction or in this direction. And those two different directions, the positive velocity and the negative velocity, cancel each other out. And so you have no net momentum. We expect the particle to be found right in the middle of the box. And then, of course, there's diminishing probability on either side of that. Okay, very cool. So now what about this expectation value of the momentum squared? Well, if we were to carry out the expectation value of this momentum squared, we get n squared h squared over 4l squared. Well, why is that significant? Well, I'll remind you that kinetic energy is equal to p squared over 2m, right? That's another way of writing 1/2 mv squared. Check out what happens to this result. So the expectation value of this particular wave function, right, is n squared h squared over 4l squared. So let's write that down. N squared h squared over 4l squared. Well, now, so what happens if I take this value and divide it by 2m? What do I get? Well, I get n squared h squared over 8ml squared. And look at this. It's exactly what we got from the Schrodinger equation. So all of this that I'm kind of spinning the gears, going round and round and round, is to establish that this is a good solution, that we can work with this solution, all right? It also establishes this notion that we expect our particle to exist somewhere right here in the middle, okay? And as I go up in different energy levels, okay, I still preserve this symmetry of superpositions of particles moving perfectly left or perfectly to the right, okay? And so I think I've kind of got that described here on the next slide here, right? If I look at psi squared, right, that function, so you can see it's kind of establishing the same thing that I'm showing you here with this picture. And, you know, keep in mind, we're talking about a particle that's moving like back and forth, right? And so something really cool to this, or something really cool happens when we really crank up this n value. And I want to demonstrate that over here. So in my little simulate, I'm allowing n to go from 1 to 10, every unit of 1. So you can see it maxes out at 10, okay? What if I allowed it to go up to, you know, like 1,000,000? And I'm not going to say every one. Let's just let n scale all the way up to 1,000,000, okay? What does that look like if I do that? Well, it looks like basically the particle can exist anywhere along this path, which is actually what you would expect from classical mechanics. If we're imagining classical mechanics, our particle is just moving back and forth, right? We expect that it can exist anywhere along here, okay? Well, look, if I make the n principal quantum number, if I make that 1,000,000, these probability distributions show that. And even if I go way down to like, you know, 400,000 or 200,000, right, at these humongous values of n, it's basically just showing that the particle can exist anywhere along the box. Not until I get down to these very small values, like 1 or 2 or something like that, you know, do I get these quantized exact positions where I expect the particle to exist. So that is what we call the correspondence principle, which states that classical mechanics emerges from quantum mechanics as large quantum numbers are reached, okay? And so what I also want to go back, I'm going to go a little bit over my 30-minute movie. You may have seen this GIF that's on our course homepage. This is the particle in the box problem, right? You've seen in that GIF how this particle is kind of bouncing back and forth in the box. you've seen how these solutions are evolving. So those are actually showing you the how these wave functions will evolve in time. So A, B, and C show the standing wave approximations. Panels E and F show us the actual full time solution, which is really cool. I've got a Mathematica file here that Wes Bliven hooked me up from physics. And I'll just point out one of the small elements. So here we go, e to the negative I t. So that's really the only thing that changes in these wave functions with respect to time. You can also see another function right there, e to the negative I energy I squared times t for time. So this is really cool now. So this is psi squared of our particle in the box. And what we're going to see this particle move back and forth in this box. But we're going to see what it looks like when the wave functions are evolving in time. And so let's push play. Yeah, I'm going to make it go nice and slow. And so this is really cool. We're going to see this, this particle, all it's doing is just moving back and forth. But it looks crazy because there's a confluence of constructive interference and destructive interference that's really making those wave functions appear quite funky. So I think we can speed up the time a little bit on this thing. So there we go. So it's just, honestly, this is all it's doing is just a particle that's moving back and forth as a superposition of exponential functions with imaginary exponents, okay? So this is kind of cool. Okay, so one last little bit to go through, and I'm going to end that off, okay?